Hi, it's Dr. Ben. Let's do another update. So there's another preprint out today. I think I said in the last update that those were papers. Those are not papers. They're preprints. They're bioarchive. That's where I'm looking to try and see what's coming down the pipe. And these will probably be published in a couple of weeks with some minor modifications usually, but probably nothing substantial in the ones that I'm picking out. I'm avoiding some others that I think are, I don't know, might have some more holes in them or a little more controversial, and I think may end up getting revised or possibly even rejected. Yeah, so here we go. Um, the next preprint, not paper, I want to look at is one in bioarchive. And what they're doing is they're looking at a better way to actually do the sample preparation for the test. So right now, there are a couple of tests you can do. So the antibody test is actually pretty quick if you're using one of those little strips. There are other methods that are a little more sensitive, called an ELISA. Those take a little bit more equipment and a little more time, but they're not too bad, a couple hours. The PCR test, so this is the main test, and there's two versions called the N1 and the N2, and they both work well. They're just looking at different parts of the N gene from the virus. Yeah. Both of those, both of those are going to work by actually picking up a little piece of the virus that is inside of you at the moment and copying it. And they can't copy it if it's not there. And so if they've made copies, that means it was there. And so, yeah. And so you have SARS-CoV-2. The slow parts there, or the parts where this is falling down, the parts where this becomes difficult are one, those swabs. So there were only so many manufacturers of those swabs, and there was not a giant stockpile in most places of testing swabs. It wasn't thought that that was necessary, or I think there have been different stockpiles at different times, but eventually people have said, why am I storing all this stuff? Just sell it off, get some money, let's do something else. Um, and here we are. And so those are hard to get, but those are people are working on that, and people are figuring out ways to put those together and actually make that work. So that's more like a manufacturing thing. There's no real extra science there. The next step, though, is once you have that swab, you have to get the virus off the swab, because you can't just do the PCR test on the virus. You have to do the PCR test on the stuff that's inside the virus. You have to find a way to open up that virus, and that's what is slow. So there are RNA purification kits that you can buy that involve these really cute little columns. They're about that big, and they sit inside of a tube just perfectly. It's I don't know if you like it when things just fit perfectly and are beautifully engineered. These are marvelous. The high end ones anyway. They cost a couple bucks each, and they're kind of slow. If you have like the ultimate setup, you can get through them fairly quickly. You can even use these robots basically to do some parts of that. But most hospitals do not have a robot that's just sitting around waiting to do RNA purifications. It's not something we ever needed in bulk before. And so the question has been, well, how do we speed this up, or how do we find a way to do this? So when the kits have sold out, how do we extract RNA? And there's a nice little preprint that's out, and it compares all the different methods. So they tried nothing, and they tried just heating it up, because with bacteria and DNA, that works very well. You heat them up, you pop the bacteria, and then you can just read the DNA that was inside. This virus, though, is RNA, and RNA, single-stranded RNA anyway, is very fragile compared to double-stranded DNA. It just doesn't do well in the world. And so, yeah, when you just heat it up and pop them open, it actually just destroys the RNA as well, and you don't get anything back. So that's a good way to ruin your swabs. Then they looked at a couple other methods, and one of them is just really old school. They're calling it an acidic pH lysis. And you know what? Yeah, sometimes the old methods work. Yeah, as an old timer here on what's apparently Jungle Friday. Yeah, nice new shirt. um, so the way this one will work is that you start out with it takes three buffers to actually do this. The first buffer is going to have SDS in it. So SDS is the thing in your toothpaste that makes it foam up, and it's one of the components in shampoo. I think it's the one that makes you cry when it gets in your eyes, but I don't know. Shampoo scientists can tell me I'm wrong. Let's see. And it's also got citric acid, and it's also got sodium citrate in there. So it's got a nice little buffer system. And yeah, you put that on, and the SDS, this sort of soapy, sudsy stuff, just pops the virus open exactly the same way as when you wash your hands. Yeah. And so this is just a nice little demonstration that that actually 100% works. And once the virus is opened, you have broken the delivery mechanism. There's no way to get that piece of RNA, the genome, into your cell anymore, so it is no longer infectious at all, which is great news. Then the second buffer is just going to get rid of that soap. It's basically everything except the soap and a little bit of salt in there. And so the idea is to stick lots of salt to this piece of RNA, because RNA and salt will actually, one of the components of salt will stick together. And when it does, it gets a little bit heavy. And then if you put it in the centrifuge, you can pellet it right down to the bottom. So it'll just stick to the bottom in a little salty lump. And that's great, because then you can get all your RNA in one spot, plus a bunch of salt, yeah. And you can get rid of everything else that you did not need and that could make it your RNA get broken down later on. Then the last step is you do an isopropanol wash. And what this does, it's an isopropanol ethanol mix, I think. The isopropanol is rubbing alcohol. Ethanol is drinking alcohol, for want of a better word. Only this is going to be 100% concentration of both of those, so this would like kill you probably. But what it does is it gets rid of the salt from that pellet, or at least most of the salt, and it still leaves the pellet there. And so you just put it, mix it with that, put it in the centrifuge. Once again, the centrifuge just sort of forces all the heavy stuff down to the bottom, and yeah, or all the massive stuff. And that's it. Now you have a nice little pellet of pure RNA, and you can resuspend it, which is just like you mix water on it, and then it dissolves again, like Kool-Aid powder in a thing of water. Yeah, pitcher of water on a nice day. And there you go. And so this is a pretty quick process. It takes about 40 minutes. All of the chemicals are super cheap and basic, which is a very good thing. Like things that are already present in every hospital and university, pretty much everywhere, and are not in short supply. These are not critical demand components. Things like those kits that are already very highly manufactured and packaged, those are things that are a little hard to get at the moment, but this is a nice way around it. And then they test it out and show that it's as good or, as the commercial kits. So this is very positive news. And I think this is going to make a difference for a lot of hospitals in areas where they don't just have a giant stack of these kits. They'll be able to run more tests and do them more efficiently. So hopefully this is going to be good. It's still just a preprint right now, but the technique is from, I don't know, I think the 1970s, maybe before that. Yeah, so it's been tried out a lot. And this is just showing that it definitely works on a SARS swab, which is a good thing. So thanks very much. This is Ask Dr. Ben.